Good morning, students. After Euryson's lemma, its converse, and its general form, now this video and maybe the next video will be a little bit relaxing for you because we are not going to do very tough, very difficult, very lengthy theorems or lemmas or propositions. So I try to make this lecture easy for you, understandable, and interesting as well. So the first question what I'm going to take today is that question. I'm not writing it as a theorem, so it is just a question. Show that in normal space need not be T2 space. That means Hausdorff. So this we have to show. So this is the question, and before going into the proof, I'd like to tell you that this question might be there in your examination paper in the form that give an example of a normal space which is not T2. That is another form of this question. So what we have to do, we have to give an example of a normal space which is not T2. So here is the example. Take your set X as the set containing 3 points ABC, and now consider this topology tau having the sets phi, X, the singleton set A and its complement, that means the set BC. Now look into this topological space X tau. For the proof that it is a normal space, what we need in the starting two disjoint closed sets. So let us have a look on all the closed sets possible. So corresponding to phi, the closed set is X, corresponding to X, the closed set is phi, corresponding to singleton set A, the closed set is the set containing 2 points BC, and corresponding to BC, it's the singleton set A. These are the only closed sets. These are the only possible closed sets. Now we need a pair of disjoint closed sets. So phi can be paired with any of these. So you can take phi and X as two closed sets F1 and F2. You may take phi and BC, phi and the set containing 2 points BC. You can take it as F1, F2. Another possibility is that you can take phi and the singleton set A, phi, singleton set A, you can take it as F1, you can take it as F2, and the last possibility is the set A and the set BC, you can take it as F1, you can take it as F2. So in all these four possibilities, what you need to find, these are the only possibilities, there are no more pairs of disjoint closed sets here in this topological space. So we need to find in all these possible cases a pair of disjoint open sets containing them. One open set containing the first set F1, the other containing the other set F2. In the first case, and these are your open sets, the members of the topology. In the first case, you can take your phi as your G1. So this phi is contained in phi, it's obvious, and for G2 you can take the set X because X is contained in X, and these two are also disjoint sets. So you are able to find a pair of disjoint open sets containing the given two disjoint closed sets in the first case. In the second case, once again, you can take same your F1 as your G1, phi, because phi is contained in phi, and phi is this open set also. And this BC, which you have considered as a closed set from here, you can take it an open set from here. So the set BC, you can take it as your G2 because your F2 is contained in G2. And once again, this G1 and G2 is a pair of disjoint open sets containing the disjoint closed sets F1 and F2. And the third possibility is just the same one. You can take your G1 as your phi, and you can take your G2 as the singleton set A. So F1 is contained in G1, F2 is contained in G2, and G1 and G2 is a pair of disjoint open sets. And same is for the fourth case. Your F1 is your G1, the singleton set A. So F1 is contained in G1. Your F2 is your G2, BC. So F2 is contained in G2. And G1, G2 forms a pair of disjoint open sets. So you are having in all these four cases a pair of disjoint open sets containing the given pair of disjoint closed sets. So the space is normal, is very, very clear. Now we will show that this space is not Hausdorff, it's not T2. And to prove that, we will have to find two distinct points from the set X such that there does not exist a pair of disjoint open sets containing them. And it's very easy. You take one point as B, other point as C. So what you need now, if the space is to be T2, Hausdorff, you need an open set containing B not containing C, and an open set containing C not containing B, and the two open sets must be disjoint also. So B is not here, so you cannot take your first set as phi. You can take X, but if you take X, then there is no set which is disjoint with X and contains C. You can't take A as here. You can take BC here because B is contained in BC, but C is also contained in BC then. So you are not having a pair of disjoint open sets, one containing B, other containing C. So the space is not Hausdorff. So this is an example of a topological space which is normal but is not T2. Yes, but the space is, if the space is normal as well as T1, that means T4, then it must be T2, that we have proved in an earlier video. Now, the next question I am taking to be very, very similar to this one. So, the question is, show that a normal space need not be a regular space. Need not be a regular space. So, here, this question can be asked in your examination paper as, give an example of a normal space which is not regular. So what the topological space we will have to give in this question as an example. So take your X as the same set ABC which I have taken earlier, but the topology I am going to change. I am considering this topology phi X, the singleton set A, the singleton set B, and the set containing points A and B. You can check, it satisfies all the four axioms of a topological space, so it is a topology, no problem. Now what the closed sets are? Here the closed sets, all the possible are X, phi, BC, AC, and the singleton set C. These are the only possible closed sets. For the normality, to check the normality of the topological space, we need a pair of disjoint closed sets. So I think the only one possibility is phi with any of these sets. So you can take phi as one set, and you can take the other set as any of these. Your A can be X, your A can be BC, your A can be AC, your A can be C, and there is no other possibility because these two are not disjoint, these two are not disjoint, these two are not disjoint, and any two from these three are also not disjoint because C is there in all of these. So these are the possibilities for your F1 and for your F2. Now you need two open sets, one containing this, one containing any one from these, and the two open sets must be disjoint, and it is very easy. You can take your G1 as phi for all these cases. So your phi is contained in phi, that means F1 is contained in G1, and here you can take the set X as your G2 because X is also open and X contains every one of these, and phi and X are also disjoint. So you are able to find a pair of disjoint open sets containing F1 and F2. So the space is normal. This is very easy. Now the second part, that to check the regularity of this topological space, we will show that this is not regular. That means we will have to take a closed set and a point not belonging to that. So if your set is phi and you want to take A not belonging to phi, or B not belonging to phi, or C not belonging to phi, then once again you are requiring two open sets, one containing phi, other containing these sets. So you can take phi and x again. So your phi contains this phi and this x contains every one of these. So this is the first case when your set is phi. Okay, you cannot take your set as x because you need an element which does not belong to the closed set, and that does not exist because x is a whole set, universal set, and x contains all the elements. So you can take BC now. So if you take BC as your closed set and A not belonging to BC. Now there is only one open set that contains this. So X contains this. So this is your G2 if it exists. But the question is, now you want to have G1 here that contains that A, but no possibility here. No possibility. Whatever the set you will take A, then A and X are not disjoint. If you take here AB, then AB and X are not disjoint. If you take here your X, then X and X are not disjoint. So this is a particular case. This is a particular case where you are having a closed set and a point not belonging to that closed set, but there does not exist a pair of disjoint open sets containing them. So that means the space is not regular. So here is the example of the topological space which is normal but is not regular. So one or two more questions I'll take in this video and then we'll move on to the next video. So another question what I'm going to take is that, prove that, what about indiscrete space? What about indiscrete space? Is it normal or not? Because we are basically doing normality. So we have to check whether discrete space is normal or not. You take any set X and the indiscrete topology, you know that it contains only two sets, the phi and the set X itself. Now to check the normality, you need two disjoint closed sets, and the closed sets here are, these are the only closed sets, phi and X. Okay, these are both disjoint, no problem, because their intersection is phi. This is your F1, this is your F2, you can take like this. And you are able to find two open sets X, G1 containing X, and G2 as phi, because phi is contained in phi, and these two sets are disjoint also. So you are able to find a pair of disjoint open sets containing the pair of disjoint closed sets. So that means the indiscrete space is also normal space. Okay, another question comes to our mind, what about the discrete space now? And especially discrete space with at least 2 points. With at least 2 points. So is it normal or not? So let X be your space and denote by D the discrete topology defined on X. And now we know that in discrete topology every set is open as well as closed. So if you take F1 and F2 as your disjoint closed sets, if you take F1 and F2 as your disjoint closed sets, the same sets G1 and G2, that means F1 is equal to G1 and F2 is equal to G2. So F1 will be contained in G1 and F2 will be contained in G2 because they are same. F1 is same as G1, F2 is same as G2. If F1 is closed, then it is open also. If F2 is closed, then it is open also because it is discrete topology. Every set is open as well as closed. And if F1 and F2 are disjoint, then the same sets G1 and G2, they are also disjoint. So for every pair of disjoint closed sets, you are always able to find two disjoint open sets containing them. That means the space is normal. That means every discrete space with at least 2 points is a normal space. So here I am going to end this video. In the next video, we will do more and more questions on normality, regularity, etc. Thank you once again.